So, welcome everyone to our paper reading on an important paper that is usually referred to as CLIP. The title is somewhat long, Learning Transferable Visual Models from Natural Language Supervision. The value or this paper is a big milestone in the journey of AI. It is one of those breakthroughs that pretty much ushered in the field, a very, very hot subfield in AI called multimodal learning. Right? It is a realization that what we consider language can span beyond text. Language is there in pictures. A picture says something. A video says something, of course. That's why we watch videos. We see language. Audio is perhaps the most common form of language. We speak far more than we write. And language has many forms. There's sign language, there's language in gestures, there's language expressions. Things are said in the tonality of how we say it. Many things. And the AI is now beginning to, as we get into this new world, it is, guys, one of you, could you please close the door? It swung open. So it's beginning to span all of these various modalities of language. So remember, these are modalities. The word people use is modality. Text, images, video, audio, right? And now, obviously, we are getting into some specialized domains like gestures and sign languages and so on and so forth. One of the internship that was done here last summer was by a very bright student. He did for sign language, and essentially to be able to, in near real time, translate from sign language to spoken words and so forth. Translation and spoken words. I believe he was trying to do it in multiple languages at the same time. So quite a few things. So this paper. So
what's the sign? Was it a video of the sign language or just images?
American Sign Language.
But it was a video of the sign.
Yeah, video of somebody gesticulating, and you could in real time watch the video and convert it to spoken language in multiple languages. If you guys feel that will be a fun exercise, I can easily make it the bootcamp thing. It's very doable actually. It's not as hard. It's doable, right? But it's a challenging problem. It's not something that you can do overnight. So, all right, we are going to do this paper. To give you a background, as always, what I'll do is I'll give you the core idea of this paper. Everything is captured in this image. So we are going to spend quite a bit of time deconstructing what this image is trying to say. It says a lot. In fact, everything the paper says in one way or the other is already spoken to by this image. Last time the title of the paper was a 16 by 16 pixel patch is worth, what was that? A word is worth a 16 by 16 pixel, right? Yeah, it was a play on a phrase that image is worth, a picture is worth 1,000 words, right? That is certainly true of this image. This image says a lot and is iconic in the sense that it ushered in pretty much, is one of those papers that ushered in the field of multimodal learning in AI. So let's get to it. I realized I would like to sit today as I'm doing this paper, so bear with me as I lower the table. So are you guys still, those of you who are remote, are you guys still able to see me?
Yes.
Can you zoom in a bit on the TV?
Yes, I will do that. I will make it a little bit more conducive. Let me situate myself. I think little bit.
Sorry? Yeah, yeah.
All right. So I have no idea what if you guys can see me properly. I assume you can. So I'll just go with that assumption. See, we know that in an encoder part of the transformer, suppose this is the encoder. Remember, a transformer is an encoder decoder block. Right? So if I give it a text, the cow jumps over the moon. This goes in. So this will go in as all tokens. It will get tokenized. So what are the steps? It will get tokenized and it will go into the transformer. When it goes into the transformer, the encoder part of the transformer, what will it come out with? It will come out with what in sequence to sequence models, or what I call language models. Just a recap. What was the basic idea of an encoder? Hidden representation, a latent language representation, and it goes into a decoder. So X goes in, encoder. What comes out of the decoder could be, for example, a translation. It could be a summarization. It could be continuation, right? So it's a completion, and so on and so forth. Or maybe it is re-rendering that text into poetry. It could be whatever it is that you want it to be, right? So, but the core of it was a latent representation, right? Now, encoder therefore produces a latent representation, roughly speaking. That's the core idea of an encoder-decoder architecture or a language model. This is a recap. Now we know that if you take, for example, a bird, for example, bird. Bird means anything in the bird family. If you recall, we did bird, Roberta. Did we do that? But yeah, all of these architectures. So any one of these encoder architectures will produce a hidden state, isn't it? Now, this was the standard bird. This is a recap. We also did something which is different. It is called the sentence encoder. That takes the idea one step further. It takes the idea of an encoder, let's say, think bird. And what it does is it juxtaposes it with the idea of a contrastive loss function. Contrastive loss functions have been around for quite some time in machine learning. What it means is, what is contrastive loss? You tell it, you always give input as triplets. You give X, you give something similar to X, and you give something random, completely orthogonal, has no relationship to X, or at least you don't intend to have a relationship to X unless accidentally, right? So primarily what it means is you need to have X, you need to pay some attention to finding something that is actually similar to X, and then you need to randomly pick something from somewhere and say, okay, that's a random data point. Right? Whenever you do that, what can you do? If you have a notion, if you have a notion of distance or similarity, and these words are antonyms of each other approximately, you could do this. You could create a loss function whose goal is, it says, it looks at the divergence between X and S. It says that X and S, we gave it to you to mean the same thing, right? So when you compute these vectors, let's say that these vectors come out, like these things come out, actually not X, let me write it this way. The hidden state of H, because X will become, through the encoder, the hidden state of X, isn't it? The S will go and become the hidden state of S, and the R will go and become the hidden state of R as it goes through the encoder. We agree with that, isn't it, guys? So here is your encoder. It goes in this, and what comes out is HX, hidden state of H, the hidden state of S, the latent representation, and the latent representation of the random vector. We get 3 vectors, isn't it? But we do know that by construction, the way we constructed the data set, we made X and S nearly identical. So what do we want? We want the distance between HX and HS should be ideally 0 or as small as possible, isn't it? So any non-zero value is effectively a measure of a loss or insufficient learning. One intuition about loss is always, it's a measure of not yet fully learned, isn't it? So this is your loss there. And then the opposite is also true. You want to minimize this, and you want to maximize the distance from HX to H random, isn't it? The random vector has no business being anywhere near HX. Does that make sense? So if you could do this, you will end up with what you call a semantic embedding. This is a recap of what we have done in the previous weeks, isn't it? You will end up with not just this H not only belongs, this latent representation, let's say that H belongs to, HI belongs to some representation space. For n, but let's take, or some d-dimensional latent space. But imagine it's 2-dimensional space. What you do want is X to, if this is X, you want S to be somewhere here, and you want random to be somewhere like this, R. That is how you would want it to get projected, right? That means that the machine has learned, isn't it? On the other hand, if perchance X and R are nearby and S is far off, then you're not doing good, right? So what your objective is to minimize, to train the machine to minimize the distance between the X and S and maximize the distance between X and R, right? Or another way to put it is to maximize this distance is the same as to minimize the negative of that distance, isn't it? And so you can write the loss, triplet loss, contrastive loss as D, or minimize both of these. So actually loss you always try to minimize. In machine learning, most of the libraries, they give you a minimizer or an optimizer. So you can write it like this, HX, HR. Now, pay attention to it, guys. If any part of this doesn't make sense, you have missed something foundational. So please correct me. So this becomes your loss function. And your goal is to minus L. Right? This is the heart of contrastive learning. Right? So this is a recap. And so in other words, you want to find those weights and biases of the encoder W star, sorry, I should turn off the touch. Okay, W star such that, right, it is the argmin W of the loss. Loss is a function of the weights and biases, isn't it? So it is the loss. encoder weights and biases. So you want to find those weights and biases in the encoder, right, that minimizes, and by W, I also mean B, all the B's also, that minimize. So you will often see in literature terminology written like this, argmin, right? Argmin means which value of W will minimize L. Are we together? It's a very succinct way of saying which value of W will minimize L. Whichever value of W, the W matrix minimizes L, is your properly trained weights of the encoder. Right? So far, is it all very intuitive? Are we all together?
So when we say are the weights.
Weights and biases.
So weights is a plural word.
Plural, yes. So it is remember, your neural network will have lots of neurons all over the place. And we are talking about the weights, each of these weights, and lots of weights are there.
So at each layer, or even
the whole thing, the whole machine, the whole encoder, everywhere that there is a learnable parameter, right? W is a proxy for all of those parameters. It stands for all the parameters.
That matrix.
That entire matrix, you can say, yeah. Entire matrix. It is actually many matrices, but okay, one way of thinking of it is the whole matrix of weights and biases within the encoder.
More higher level clarification on which framework does what, but itself encompasses this contrastive learning, or is separate?
No, BERT has nothing to do with this. BERT is just an encoder architecture. Right? Now, this is contrastive learning. This is the gist. You can do contrastive learning with anything. If you want, you can do it with, all over machine learning, this contrastive learning has been used quite a bit, right, for different purposes. Oops, sorry.
One quick question there. Why should we have the distance between HX and HR as a minimum in the loss?
1 second, guys. I don't know what happened. Just now the picture has disappeared in OneNote. Before I answer, let me try to recover. What's happening? It's on the top. It has scrolled to the top most likely. Yes, you're right. Oh, I need to zoom in. Oh, there it is. Somehow it has
It zoomed out completely.
and it has gone down. So a lot of space has come up. So bear with me for a moment. It is not letting me scroll down. I've seen this happen with OneNote. I'm going to close OneNote for a moment and restart it. Much better. Okay. With Windows, that seems to be the mantra. Anytime you get into trouble, restart. So anyway, what was the question that somebody asked?
Yeah, I asked that question, Asif, so in the loss function that you have, so you said it should be the difference between HX and HS minus HX and HR. Why would HX and HR difference be minimal? It should be maximum, right?
Yeah, so to maximize the difference is the same as to minimize the negative of it. Sorry, to maximize the distance between HX and HR is the same as to minimize the negative of that distance, isn't it?
Oh, okay, got it. Thank you.
That's the basic intuition. So now what I'm saying is, and again to Ramki's question, see, BERT is BERT. All that it does is it produces a hidden representation, right? But when you put the BERT idea together with contrastive laws, you can do something very interesting. BERT happens to be the encoder you use, a very powerful encoder for words. But when you put it together with sentence encoding, or with this contrastive laws, what do you get? You get a text embedding that puts similar text together and a text that are unrelated far apart. Does that make sense? And that was the foundation for us to do encoder plus contrastive learning is equal to sentence embedding. if you're in the text domain for text. And this was our paper. This was our S-BERT. For example, this breakthrough came from the S-BERT paper. See, guys, the word S-BERT is so closely related to BERT, people often get confused as BERT. It's not BERT. It is encoder. They happen to use BERT, right? Because obviously it's a good choice. BERTs are good choices. And contrastive learning. You put these two ideas together to get, and what was the consequence? If you could do similar vector representation, the consequences of this simple idea were tremendous. It led to a revolution. It led to, for example, now what I could do is I could take all my documents, D1, DK, and embed it all over this latent space, right? It becomes the space of meanings of that text. Right? What the contrastive loss does is contrastive loss's contribution is loss contributes or imbues the latent space with semantics or meaning. And just sit back and ponder over the significance or the enormousness of the statement. The fact that you can do it with just a well-known loss function that's always been around, and you juxtapose it with a transformer encoder, and you get that. Because the moment you can imbue it with meaning, now what happens? You can do search. If you want to search for a document, if you have, and this is a recap, if you get a query, you convert the query into a query vector using a encoder, hquery. So query becomes hquery using the encoder. And what do? You just go and say, okay, here is the hquery, it lands here. So all these neighboring points, they must be what the user is looking for. Those documents is exactly what the user is looking for, because their meaning, their semantic content maximally aligns with the query. Does that make sense? And thus an AI search engine. Right? So that is a recap of what we can do with text. Then the question comes, and this is the question that is being asked in this paper. What about images? Didn't we just find a way to convert images into words by taking the patches? Like, you treat the entire image as a sentence effectively. What was the contribution of VIT? Do we remember visual transformer? Who would like to articulate that?
We had images, we converted them into patches, then converted each of the images into vectors.
That's
And
right.
then put it
That's
into-
right.
There was also a class hidden state there. That we didn't put
That's
as
right.
well. That just does the classification of the image. And then we just put it
Excellent.
in the encoder, no decoder.
Yeah. So what you do is you create 16 by 16 pixel patches. They become the words. And the entire picture can be thought of as a sentence. Right? Now, I must say one thing. I only introduced the VIT for paucity of time. I didn't cover its subsequent developments. See, 16 by 16 is an arbitrary. Do I hear someone with a question? Okay. So 16 by 16 is an arbitrary choice. It's a good choice to prove a point that you can do it. But people realize that sometimes a 16 by 16 itself has enough local information that when you just linearize it, you lose something. Oh, by the way, speaking of the VIT paper, I would like to make two corrections that I wanted to do. One was when I was talking about, remember that last week, actually, I just come back from travel. Guys, can you please mute yourself?
Hey, Asif, Jay is, I think, driving, so you
Jay
can.
is driving, sir.
Okay.
Jay, mute yourself.
All right. So
Do you want to be recording the session?
Jay, turn off your camera, please.
recorded. Yeah. All right. Now, guys, let's continue. So I made actually two small mistakes. It was perhaps underslept or whatever. That paper I was reading after a long time. I mentioned that there is a special token CLS. And for a little while, I was confused that, okay, how do you get to the embedding of that? It's learned, whatever it is. No, it is very simple. You just throw in a, so first correction that I want to make is, you have a dictionary of words, just dictionary of tokens, right? Cat, dog. They all map to, in the dictionary, to some index ID, right? Let's say one, I'll just arbitrarily pick some number. I don't know what that is, or 172 or whatever it is. In the same dictionary, you just add this new words, the special tokens like end of sentence, beginning of sentence, etc., etc. What you do, or empty padding. In the BERT architecture, you just add these separators, right? A few extra tokens, and they all have their IDs, like whatever, some particular ID. I believe beginning of sentence is 101, end of sentence typically is 102 in the BERT architectures. Roberta, for example, uses this. I don't know the original BERT, what it did. Padding will have some value. CLS will have some value. It is just, you just add these things to the vocabulary, right? So, and there is no other magic to it. So now the new way of thinking is all the embeddings, all of these embeddings are learned. So these things, these IDs, they become embedding vectors, word embedding vectors, or token embedding vectors. Token embeddings. In the process of training the transformer, even those embeddings are learned. But if it helps your intuition, you can, in the beginning, think, okay, if the embeddings were not learned, I could use an older technology like word2vec and feed it in. But actually, in reality, since everything is learnable through backpropagation, even those are learned. So that is one correction I would like to make. The other one, yes.
So they are not a constant value. That's also something has to be learned for the CLS viewers.
All of them, they learn the vector. So it becomes a vector, right? Any word, any token becomes a vector of, you can choose how many dimensions, let's say 300 dimensions. Right? It will, once the machine has learned, it will become a fixed vector. But what vector it is, you don't a priori give it, you let it learn that also. That's what it is. Ranki.
Is it fair to say that while everything is learnable, by providing some dictionary or speeding up the process?
No, dictionary just says learn only these words. Dictionary just gives you a finite set. Right? See, it is important because you can't have unbounded sets. No? Yeah, you have to start with a finite set. So what happens is you always pick tokens from the dictionary. What if you encounter a word outside the dictionary? You're somewhere in there is a reserved token, other, or something like that. And you just assign any words that you don't see to that other. Right? Now, why is that okay? The reason it is okay is because
It's unknown. Unknown.
It's unknown. Yeah, it's unknown. Yeah, it's unknown or other or unknown. Known. The reason it is okay is a word's vector, initial vector, doesn't matter much. It will go through attention layers. And what will attention do? It will acquire meaning in terms of other words in the sentence, which are known, which are in the dictionary. So the moment I say, the blank jumped over the moon, pretty much the sentence is a giveaway. We are thinking cows, isn't it? That is it. So even if I put an X there, X takes on meaning, right? From all the children's stories, that it must be about cows. Or more specifically, if you say that the greenness of the leaf, right, of the hyphen comes because of chlorophyll, so whatever it is, then you can pretty much infer that whatever word is there is the leaf. because leaves are green. You have given all the attributes of the thing in there. So it is okay to do that. Any other question? Yes.
So you have a dictionary of, let's say, 64,000 words, and then those are converted into vectors.
Vectors.
But the thing is, you just said, I'm trying to grasp this, and I'm not fully clear about how it got embedded to a vector, but I thought we would be calculating it, but you said it will learn it, right? So I'm
No,
not sure.
word vector. So let's go over this slowly, guys. The cow jumped over the moon. The cow jumped over the moon. Each of these tokens first becomes an ID, right? ID. So this is the first translation into IDs, two IDs.
Yeah.
These IDs become embedding vectors internally. Each word, each token vector becomes the e-cow.
But initially,
Wait a minute.
Okay.
Do you understand this part?
That part I get,
this? Yeah. So go slowly with me.
Yeah.
Don't jump ahead.
Yeah.
This becomes embedding vector. To this vector, you add the position vector. You remember that position embedding you add.
Okay.
What is the position in this sentence, right?
Right.
These two you concatenate and you feed it into the transformer encoder. What will you get? You will get a hidden state for each of the words, right? You will get a hidden state for you'll get a hidden state for the cow, you'll get a hidden state for the jumped, etc., etc. Right? Now, and you will also have a special token, CLS token, right? That also will come out at CLS. Now, at this moment, you have a choice. You can look at this token. So you have two basic choices. You can either look at this vector and just take that vector and say that vector represents the whole sentence, right? Because it was an empty vector, it's paying attention to the whole sentence. Or the other thing you could do is you could mean pool it. Mean pooling means average all these vectors, right? So if I just average if I do the H average of all the, then in either case, I want to get one vector. That vector represents not the words, not the position embeddings or word embeddings. It is the embedding for the sentence. That's what I'm saying.
Okay.
Now you got that?
Yeah.
Oh, that's it. Yeah. So you have to remember that machine learning is all about vectors, and soon the confusion you're going through is very natural. In the beginning, it becomes hard to tell what am I talking about? Which vector are we talking about?
Yeah.
Right? So you have to go slowly, diagram it out. You say these are the token vectors. Here, token vectors are here. These are the position vectors. And all machine learning is just a bunch of vectors and transformations and activations of them. And these are the sentence embeddings. At the end of it, you have to pick one and say, it is the embedding for the sentence. Now we got that, right?
Yeah.
Yeah, that is it. So now, guys, this is a recap of what we have done about sentence embedding. Now we also know, anyway, so let me go back and make the two corrections that I was making. So we do realize that CLS and end of the sentence and beginning of sentence and parts, they are just tokens you add to the dictionary. They will develop some ID and their actual word embeddings, so token embedding will get learned. The transformer will somehow learn it.
I have one more question. Sorry for interrupting flow.
Mm-hmm.
The token vector, right?
Mm-hmm.
So did we calculate the values in the token vector, or was that also learned?
That was also learned.
Okay. So that part I didn't understand how it got learned.
Yeah. So there used to be, actually the great breakthrough in 2014 was a set of algorithms using neural networks called word embeddings. Tokens and words are sort of similar. Yeah. So after that, it became word piece embedding. So that's why we use the general word token. Like running just becomes run and /ing, the gerund, and so forth. Right? So but token and words are more or less the same thing. Word embeddings. There was word to wear, glove. There were whole Poincare embeddings and this and that word embeddings. The limitations of those embedding vectors. So why is it that we don't just use that? and feed it into the system? Why do we have to learn it? Is the question. What people in the beginning, I'm sure they must have just started out with word embeddings itself and fed it in using word to vec or whatever. But gradually they learned that, hey, back propagation, if we can train the transformer, all the weights in the transformer, what prevents us? There is no barrier to back propagating all the way to the embedding vectors themselves and train them. Okay, right? So let even the embeddings be learned. So the modern way is that even the token embeddings or word embeddings in the transformer architectures, you just say that go figure it out. Okay. So that is it.
So do we initialize with random numbers or
Everything is initialized random. But the question is random and random are not the same. In machine learning, it turns out how you generate random numbers is also matters. Most of them, while in normal computer science, you just take uniform randoms, in machine learning, you almost always sample off a Gaussian. You take a random, so you take X sampled off. So by the way, whenever I use this notation with this wave symbol, and I use this very scripted N, this statement is cryptic. So let me just unpack this statement. Can somebody say what this statement stands for? Right? This is sampling off, sampled from, sampled from. Whenever you see this tilde symbol, right, it should mean to you in literature that you are saying X is sampled from, right? This interval 0 to 1 looks simple, right? Actually, it is not 0 to 1. Sorry, I apologize. It's not that. There is this Gaussian function, bell curve. A bell curve which is centered at 0 and whose variance is 1. Sigma square is 1, and of course, sigma is 1, right? Mu is 0. You remember a bell curve? It has a mean, it has a center, and it has a spread, how spread it is. So a bell curve, now you think of it in 1D, one dimension, this is the bell curve. Now you generalize the bell curve to arbitrary dimensions, D dimensions. So a vector, if you say I have a vector X that belongs to a D-dimensional space, right? And you say, take this vector, sample it off the bell curve. Means sampling off the bell curve means sample in such a way that values closer to 0 are more likely, because this is the probability of its happening, probability density. So it's just a digression into statistics. You're more likely to pick values closer to 0 than far from 0. Right? You don't uniformly sample. So when you populate the X vector by sampling off. So what does sampling really mean? Here's the physical intuition, guys. Children make, when you go to the beach, and obviously we are blessed, beach is always nearby here. Oh goodness, tomorrow I better go there. So it's been a while. So you could, well, I suppose I'm still a kid. I like to play with the sand. So a lot of my mathematical intuition comes from sand. So I keep using the word sandhill. So you make a little sandhill, nice, smooth sandhill. That's basically your normal distribution, two-dimensional normal distribution, right? So now think of it. You have made a sandhill inside a box. So you have finite amount of sand, just 1 unit of sand. But most of the sand is concentrated in the hill, right? So now think of it this way. In the bottom, the plate on which you have made the sand hill, let's say this is the plate. This has a coordinate system associated with it. X, this is your 0, 0, right? And this is your X2, this is your X1 direction. Think of XYs if you want to think. And right in the center is the peak of your sand hill. Now ask this question. If you sampling of this distribution is as simple as randomly picking 1 grain of sand from this heap. So when you pick a grain of sand, where are you much more likely to pick it from? If you take a random grain of sand that has come from this pile, where is it more likely to have come from?
Center.
From the core of the hill rather than from the periphery. In the periphery, there isn't enough sand, right? So if I just give you a grain of sand and I said, where did it come from? You're better off assuming that it's somewhere in the central region, isn't it? So that is it. So that is sampling from a distribution. So whenever people use these big words, mathematical words, so I get scared. So then I go back to my sand heap, right? And I say, okay, now if that distribution were a sand heap, what does it mean? And what it means is something very simple. It means I'm just sampling off that sand heap. Right? I'm just asking this question: if a grain of sand came from that heap, where is it more likely to come from? What's the problem? It is less probably coming from the periphery, or more probably coming from the core of it, isn't it? That is it. And now you can shape your sandhill in all sorts of ways. So, for example, if you shape your sandhill like this, right? This sort of shape is also very common. It is log normal, Poisson, beta, gamma, a whole class of distributions. They have roughly this sort of a shape, right? And so you will see in machine learning, people use all sorts of distributions, right? This is called normal distribution, and therefore the word n. So now we understand the meaning of this word x sampled of a normal distribution. Are we together, guys? So to answer your question, how are the weights initialized, whether they're embedding? Whenever any parameter is learnable in machine learning, you almost always sample it off a normal distribution, isn't it? That's all it means. What it means is that every element wise, you just pick from a Gaussian, from a bell curve. That's what it means. So, all right. So I was making a correction, a digression. So this is getting a little bit off track. So I wanted to make a correction. Somehow, I don't know how it slipped in, but it is as simple as that. There is another actually error that I made last time. I just said that when you have a patch 16 by 16, right? And I went back and listened to my video, and I realized that I put my foot in my mouth there. So I said that the way you convert it into, you linearize it. Remember, I said that you can linearize it into a vector. So it becomes like a word vector, a token embedding vector, right? E token. It's like a token. You treat this as one token, one word. And so it becomes this. And the way I said you do that is, I said, oh, it's very simple. Just read the first row, the second row, the third row, the fourth row, the fifth row. Right, and that's one easy way to linearize it. Actually, well, that itself is not quite wrong. That's not what you do. What you do is, suppose I multiply the 16 cross 16 matrix. It's a matrix, isn't it, of pixel values, right? Matrix M of 16 by 16 with any, think of it this way. If I multiply it by 16 by 1, another matrix W, let me just call it a projection matrix, 16 by 16. What you will get, you can convince yourself that it will be, let's say that instead of 16 by 16, let me take 2 by 2 to get you the point. Suppose I have 1, 2, 3, 4, and I'm multiplied by, let's say 5, 6. Right? So I'm multiplying a 2 by 2 matrix with a 2 cross 1 matrix. What do I get? You will get, 5 plus 12 here, and you will get 15 plus 24 here, right? And so what you will get is a 17 and 39. And what did you get? A 2 cross 1, right? And so what is it? This is just a vector, isn't it? A column vector. We think of vectors as column vectors. So you have linearized it, isn't it? So what you can do is you multiply your 16 by 16 by any projection matrix. So long as the projection matrix is 16 cross 1, it will give you a linearized vector. It will linearize it. Are we together? Right. And one special case of that would be you can do the way I scanned it. Right? You can try it like that. Yeah. But this is the general idea. That's a correction that I wanted to make.
Yeah,
Question.
this 16 by 16 I thought was are you using sentence and token interchangeably?
Yeah. Right. So in reality, it's a picture, right? So here's a cat. Here is Vasanthi. Well, not you, but let's take a cat, right? So this looks like a cat. Here's a cat. And here's a tail of a cat. Now, what you do is you take a patch. Let's take a patch. This is your 16 by 16 patch. Are we together?
The whole picture is not 16 by 16.
No, the whole picture is not. So again, once again, I will say this. You take cut a picture up into 16 by 16 patches, a grid. What you do is, so in case you guys, so it seems that some of us missed it. So you divide the entire picture into 16 by 16 patches. We use the word patch in this language, 16 cross 16. Right? And if you multiply a 16 by 16 patch with a projection matrix, right, you can easily project it down to a linear vector. Right? It's a generalization of what I said, just scan it like that. So that was, I suppose, well, there's no excuse for making that mistake. I happen to have come from a late night flight and then showed up in the morning for this.
It is 16 by 1 come.
A vector is that, no? So if you multiply, see, look at this. A 2 by 2, if I multiply by 2 by 1 matrix, what do I get? I get a vector.
Last one.
Yeah. So in the same way, if I multiply a 16 by 16 with a 16 by 1, we can do that.
Yes.
Let me make it even more explicit. So suppose you have numbers like this. 16 by 16 is here, and I multiplied by, so there are 16 elements, A11 to A116, right? And here it is that 116, 16 comma 1 and A 16, 16. This is your matrix. If I multiplied by anything that is 16 by cross 1 here, what will it become? It will linearize it into a vector, isn't it? That's all that is meant.
This is your projection.
It's just a projection. Yes, go ahead.
So for 16 by 1, what kind of example are we multiplying for 16 by 16? What kind of
What values?
What kind of values?
Oh, you let the machine learn it. You just say, I will have, let me say W1 all the way to W16, and let the machine learn what's the best way to project images down to it. Right? So the beautiful thing is, and this is one of the things people learned in deep learning, it's sort of one of the lovely freebies, that so long as your back propagation continues and you don't hit a barrier, just about everything in your path is learnable. One analogy that I can have is, in agriculture. So for example, here in California, Central Valley, you know that there's a big canal that goes through. And if you cut open the canal somewhere and water starts flowing, it just floods the whole plain, isn't it? It's like that. Back propagation is like that. Everything in its path gets sort of nourished in some sense, because everything becomes learnable in the back path of that water. Right? That's the beauty of neural networks.
So it's sort of like pictures. So one area is going to picture, and the other areas are going to have words, and they do those learnings all together, right?
That's what this paper is about. We're coming to come to that. All right, guys. So those were the two corrections I wanted to make from my last time. But now, after a long detour, so should we call this the preamble to this paper and then start with the paper again? Okay, go ahead, Raja.
So last week you also talked about reducing an image, like a large image, to a 16 by 16.
No, I talked about chopping an image into patches like this. So here is Vaishali's pet cat.
Yeah, I mean, this is understandable.
Vasanti's pet cat, sorry.
Chopping also,
Yeah.
pet cat. But also,
Any
I thought
image-
We talked about reducing a large image, like compressing a
That's what
large
I thought
image
too.
into small. It might look like a blob, but the machine can understand that it's a
Absolutely.
cabbage.
So those architectures will understand. That is data compression or data encoding. We'll come to that.
Okay.
We haven't come to that. In
Okay.
fact, are you in the
mentioned
Tuesday
it in
class? Were you in the Tuesday class?
No.
Then I don't know where you heard me say that, but yes,
I
encoding.
heard you say that.
Okay, so we yes, those are, for example, encoders do an amazing job of information compression. Right? We will come to it when we do. We'll do quite a few other things, and we'll come to it. Or CNNs do it, for example. They extract the essence of things. There are many things that do it, but let's not go there. It's not in the direct path of this paper. So those are all doable things, but not related to this topic. So guys, do we realize that any picture, no compression, we just chop it up into 16 by 16 patches. Those patches can be made into words or tokens, token embeddings, right? Can be treated as tokens, and therefore you can get an embedding vector. As simple as that. So the gist of the VIT paper was that you could convert an image into patches. Those patches can be treated as words, and therefore the technology of the transformer, and in particular the encoder part of it, can all be applied to it. Are we clear, guys? That's all. That was the gist of that paper. And then that opened the floodgates for transformer to be used for computer vision also, not just natural language processing. That was the great contribution of that paper. Right? Now, that paper led to a whole lot of subsequent work. I will just briefly summarize that work. Yeah, and then I'll stop this video and start a new one for this paper. So what it started out doing is, people first began to critique that why 16 by 16? Right. 16 pixels is a lot of pixels, right? For all you know, in that image, it may capture the entire nose of the cat, right? Or something like that. So there's a lot of visual information, and when you just project it down to a single vector, you are losing information. So then, if you really think the heart of transformer is paying attention, so you can say, what if I treat that 16 by 16 pixel itself as a sentence and each pixel as a word? Then there could be attention between the pixels. Does that make sense, guys? And so it led to a remarkable paper, which was literally called Transformer in Transformer, TNT. Not the explosive kind of TNT, but a transformer in transformer. Explosive. In transformer and T, right? So we are a bit more a non-violent kind of people. So our TNT is different from the common TNT, right? So transformer in transformer. The other paper, and I leave that, I'll post it to the portal, but I'll leave this as an exercise for you to read on your own. Or maybe I can do it in the Wednesday paper reading. The other thing that came out is actually a very influential paper that removed a significant deficiency, the same problem of 16 by 16 in a different way. It was called sliding window transformer. And what it did, and it uses a hierarchy of scales. What it does is it says, no, let's start with 4 by 4 pixels, right? And then hierarchically, we will create overlapping, just like CNNs. What CNNs do, and I didn't quite tell, but I said that the CNNs, the convolutional, did I talk about that? Yeah. Convolutionals are followed by pooling. And what the pooling do is that they reduce the feature map gets reduced in size, but that increases the receptive field. Increases because the next layer, now it sees a little bit less local. It sees a slightly less local view of the picture, right? More higher level view of the picture. So that is important. So in a very similar way, it brought in the concept of sliding windows and then merging these 4 by 4. So that's a very famous paper. It is the swing transformer. I would love to cover it, time permitting, but at least for now, let me just leave it as a bedside reading exercise. So any sleepless night, you're having trouble sleeping, open this paper and start reading it.
Very easy.
No, I'm kidding, by the way, and that's disrespectful. These are absolutely amazing paper. If I remember right, this has close to, off the top of my head, if I were to say, somewhere between 5K to 10K citations. So more than 5 or 10,000 research papers have quoted this paper.
So in computer vision, the sliding window compression stuff was there like years ago. So this is like build up on that.
On the transformers. On the visual
that
transformers.
concept to transform.
Visual transformers. See, sliding window has been there in information theory for the longest possible time. It is inherent there. You know? So it's bringing those ideas into this. So anyway, those are the two things I wanted to mention. And so what I'll do is I'll stop this. And so I'll treat the current session that we have just been through as a grand recap of everything we have done in this workshop so far. Is that a fair statement?
Yeah.
Right? All right. So I'll call this a recap. Let me stop the recording and we'll start a new recording after 5 minutes.